So what are the options in here? Well, the options are either to accept the firewall or identify some assumption that went wrong. So one type of assumption, sort of general class of assumptions, is just already at the level here, where I tried to identify A, B, and RB was inside of R as sort of this sort of product Hilbert space, right? Is sort of the A equals RB. So one fixed. Okay. So A equals RB says that this equation is actually incorrect. A and RB, which is a subset of R, or a subfactor of R, they're not separate. Okay, they're actually the same space. So this analysis was kind of wrong. And if we just go back to the beginning, the purifier of B, RB, the purifier of B. So B is purified by RB. So by definition, B and RB are in a pure state. Okay, and that's exactly what we wanted, basically over here, because we wanted A and B to be entangled. So entanglements are consistent if, in fact, A is equal to RB. Okay. So this is sort of a popular thing, but it's kind of drastic if you think about it. What it means is that the inside of the black hole, right? The degrees of freedom to represent the inside of the black hole are actually the same as the degrees of freedom in the Hawking radiation. Okay. It means the inside. I mean, it's incredibly non-local. It means that when you fall through the horizon of a black hole in Falling Observer, you are now sort of suddenly in the Hawking radiation that's really far away, right? That's sort of where you end up when you cross the horizon. It means you're in the early Hawking radiation. And there are all kinds of funny things associated with that. Some people compare it to time travel because, before you fall in, you could have tried to interact with this radiation system, right? Because it's the stuff that came out very early on. You could have maybe grabbed a piece of it and carried it in with you. But then when you cross the black hole horizon, you see it again. So it's like you're going back in time. You got to influence the future before you got there because you got to interact with R, if this is actually an exactly clone. There's a related solution to this where A is not exactly identified with RB, but it has a similar kind of flavor. Okay, and this is basically the ER equals EPR fits. Okay, so I think I'm going to choose to talk a little bit about ER equals EPR for at least some part of the remainder of the time. So ER equals EPR is a really interesting idea. So what is ER? ER is Einstein-Rosen bridge, okay? Otherwise known as a wormhole. And EPR is, Einstein-Podolsky, and is it Rosen again?
Yes.
Yeah, Rosen. And this is just entanglement. Okay. And the claim of ER equals EPR is that at least in a quantum gravity theory, you can't have one without the other. They're really the same thing. Okay. Where does the evidence for this come in, and why is it helpful for the case of why is it a good way to analyze firewalls? So I'll say that ER equals EPR. It's the kind of idea that's useful for organizing thoughts. Sort of like how the principle of complementarity was supposed to be. But kind of thing that's easy to, really prove one way or the other, beyond the stuff that's obviously true. Okay. So the original, the origin of ER equals EPR comes from studying the eternal black hole, the two-sided eternal black hole in anti-de Sitter space. So that's this Penrose diagram. So let me explain what this is. So these are the singularities, right? Here is a boundary of anti-de Sitter space. Okay. So this thing is some kind of sphere across time. Okay, that's this line. And here's another sphere across time. Okay. And over here, there's a CFT. So we're going to be doing ADS CFT, sort of a right CFT. And over here, there's a left CFT. Okay. And these are just two independent CFTs. They each have their own Hamiltonian, and they don't interact with each other. Okay. But we're going to put them in a very particular state, for which the dual geometry is supposed to be this. Okay. And the state that we're going to put them in is called the Hartle-Hawking state. And it's essentially the same state that I used in the Rindler case. It's the thermal field double state. It's a state which is entangled between the state of CFT left and CFT right. They're entangled like the Rindler state, like the Minkowski vacuum is entangled. And the dual geometry is supposed to be this black. Okay. All right. So here we have an Einstein-Rosen bridge connecting the two sides of the black hole. And we also have the two sides of the black hole are entangled. And the claim of ER equals EPR is that, the reason why there's an Einstein-Rosen bridge is that the things are entangled, and these two things come together. Okay. This is basically an excuse to use the two-sided black hole to study the firewall problem and to see what it has to say about it. All right. So forgetting about ER equals EPR for a second. How would we study the firewall problem in the context of the two-sided black hole? So first, I should say that it's widely believed, although not universally believed, that the two-sided black hole, ADS black hole, does actually have a smooth horizon. Okay, that there is no firewall in this state. So it's an interesting playground to see where firewall arguments work and don't work. The two-sided black hole, we're going to assume that it has a smooth horizon. Okay. And now we can ask, how do the entanglements in the Hilbert space work? Okay. So the way that we're going to connect this with the story that we had before, where we just had a single black hole and it radiated, is the following. So we're going to do the following thought experiment. Okay. One. Start with a single black hole. Okay. Two. Let it radiate for some time longer than the page time, okay, so that you get a lot of radiation. And then 3, collect the radiation carefully. And collapse it into its own black hole. Okay, and the result of these steps, okay, maybe the exact result depends on the state that you started with and how you actually perform the procedure. But the claim is that one possible outcome is that the black hole that you started with, right, and the black hole that you ended with, well, clearly they're going to be maximally entangled, because the black hole that you started with was maximally entangled with the radiation, and then you turned that radiation into another black hole. So now you have two black holes that are maximally entangled with each other. Okay. make this approximately equal to TK. And you can ask, what does the geometry look like? And the claim is that for if you're careful enough, you might get a two-sided black hole which has a macroscopic wormhole connecting the two sides. Okay. And now we can try to apply the logic of so in other words, this black hole, it looks like there's sort of two asymptotic regions which don't talk to each other. But I could sort of imagine that this is just a model for two black holes that are really far away from each other, so that effectively they're not near each other. So the regions outside of the black hole are kind of far away. But maybe secretly, if you went out far enough in this direction, there'd be some kind of connection to this direction. Okay. So there's two black holes that are really far away from each other, but nevertheless they're connected by a wormhole, which is formed by the entanglement.
How are you going to make it radiate if it's in thermal equilibrium? In ADS, because the box black is.
Right. So so really we want to do this in. So I should say that this is very heuristic. Really, maybe you want to do this in flat space, right? With two black holes, you do this very carefully, and you get sort of a two-sided black hole in asymptotically flat space. But now, because we want to analyze these black holes, we're going to pretend that these two black holes are sitting inside of ADS and use that to analyze some of their properties. The fact that they're in thermal equilibrium is an important fact, because black holes in asymptotically flat space, if they're not in boxes, are not in thermal equilibrium, right? But at the level of heuristic argument, we're going to ignore them. Okay? We're going to say that it's not a big deal that this state is a thermal equilibrium state, whereas the real state is maybe a evaporating state. Or we can imagine putting the two black holes in boxes which simulate the ADS boundary, in the sense that they can come into equilibrium with some reflecting boundary conditions outside of them.
Okay, but they won't radiate.
That's fine. I don't think I care that they radiate. Okay. Yeah. So, I mean, the fact that they radiated was not actually important for this problem. Okay. The firewall argument, the way the firewall argument proceeded, the reason why the radiation was important is that it generated a system, namely the radiation, with which the black hole was maximally entangled. Okay. Once I have that, I don't need the black hole to radiate anymore. So the point is, here we have a black hole and we have another system with which the black hole is maximally entangled. So you may have thought naively that you could apply the same kind of arguments that you did over here, okay? Where instead of everywhere I see R, right, replace R with black hole number 2, yeah, and repeat the same arguments. And if the black hole is sort of maximally entangled with some other system, you would just, you would end up with the same conclusion. But here it's not true, okay? Here the final conclusion is that there's a firewall is not true, okay? So I know that Leonard Susskind likes to take this as...
Why is that? Why is there no firewall?
What? Oh, we're assuming that there's no firewall. We're assuming there's no firewall in this state, okay? That this particular state is nice enough that there's no firewall. That's an assumption. In fact, there was a paper I think yesterday claiming that the dual of this particular state and these two CFTs was not this geometry. But I mean, as far as things that we think are true about ADS CFT, this is one of the ones that we think is true. Okay. So in what sense is the behind the horizon stuff, from the point of view of this black hole, connected to the other system? So we're going to think of this CFT as a model for the radiation. And the kind of lesson for ER equals EPR, from ER equals EPR, or the punchline of ER equals EPR, is that this second black hole didn't have to be a second black hole. If it was just a cloud of radiation, you still have effectively a wormhole connecting the cloud of radiation to the black hole that you started. Okay. So the two black hole wormhole model is a nice way to visualize the relationship. All right. So what can we do in this two-sided black hole model? In what way is this radiation is this inside node related to this side of the black hole? Well, it's not exactly an A equals RB kind of model. Okay, so how is this different? How is it the same from A equals RB? So A equals RB says that the stuff that's located right here is actually part of the radiation. Okay, meaning it's part of the system over here. But it's not, okay? The reason why it's not is the following. So the way that people like to write it is instead of A equals RB, we write RB arrow A, and the RB influences A. Meaning you could do something to the system over here. So in ADS-CFT, we like to insert sources and whatnot on the boundary and look for things like response that was mentioned earlier today. So for example, you could put in a source in this CFT or disturb the radiation in some particular way and send in a signal, right? Which will influence what happens here. Yeah. But of course, things that you do down here do not, there is no operator equivalence between operators here and operators down here. There is only an influence, okay? And one way to see why there's only an influence is the fact that, well, you could have done something on this side to, interrupt the signal from over here. The thing that you do over here, the way it influences what happens up here depends on what happens on this side. So there's not an exact equality between things that happen here and things that happen here. Okay. Really, the operators here are made up. They have pieces on both sides. Okay. This is one of the lessons of VR equals EPR. So, so it's not A equals RB. It's RB influences A. Right. Where's the rest? Where's the rest of A? Well, it's somewhere out here. I think there's no definite answer other than, somehow these two sides conspire to make the inside. Yeah. What else can we do with this model? Well, we could try to answer the question of, so here's an interesting question which I think doesn't have an answer yet. If this is an actual model for the radiation that left the black hole, you might ask, all right, in this particular state there's no firewall, but if I send in a really messy disturbance down here, if I influence the state and send in a really messy disturbance, by the time it gets up here, it could be some kind of high energy shock wave, which effectively becomes a firewall. So someone who drops in up here is going to see the results of my high energy shock wave. In other words, how special is the state where there's no high energy shock wave? There have been some recent results in this direction by Schenker and Douglas Stanford are analyzing sort of perturbations of this Hartle-Hawking state and various shock waves that travel across them. And what they're after is the question of if you don't have exactly the Hartle-Hawking state, might you still have reason to expect a smooth horizon? Here's another possible question that you could ask in this scenario. So the radiation comes out of the black hole, and let's say you believed that if the radiation remained undisturbed, you accepted that there was a nice smooth wormhole effectively connecting the radiation with the black hole. And so when you cross the horizon, nothing happened. But now the radiation is going to interact with stuff. Okay, let's say the radiation interacts with the CMB in real life. Yeah. Does that interaction create a firewall? And this is a really complicated question because, for example, if you believe in ER equals EPR, right? If the radiation that comes out of the black hole now interacts with the CMB, it then becomes entangled with the CMB. Yeah? So now the CMB is entangled with the radiation, and the whole thing is entangled with the black hole. So now there's some kind of wormhole connecting the CMB with the black hole. And so in order to figure out what the geometry is behind the horizon, you need to now involve the state of the CMB. So it gets very complicated very quickly. Okay? If you don't want to worry about entanglement with external systems, you could imagine, without entangling, just effectively, acting with operators on systems like this, right? So I mentioned in ADS-CFT, we know how to act with certain kinds of operators, local operators which we can insert on the boundary, related to these non-normalizable modes, we turn on sources on the boundary. But if I'm just sitting there interacting with the radiation and I want to model it with this sort of ADS-CFT type picture, what sort of ADS-CFT operator would correctly model just me fuddling with the Hawking radiation? Yeah, is that correctly modeled by inserting a local operator somewhere, or is it I'm effectively inserting some really messy non-local, CFT operator that we don't have a really good understanding of in terms of ADS-CFT about what it does to the geometry? Okay. So there are lots of interesting questions motivated by this correspondence. So I think to finish up, I'm going to mention several other things that people have thought about.
Sorry, I have a question. Is there going to be a wormhole for Lindblom horizon case? There is also entangled, right?
Yeah. So in the Rindler horizon, ER equals EPR means entanglement is the same as space-time connectedness.
Okay.
I think this is something that Van Ramsdonk has been saying for a while.
Yeah.
This is sort of like a subset of that. So the connectedness of flat space is related to the fact that there is local entanglement in flat space.
So connected means the Lindblom right side of the Lindblom edge is connected to the left hand side with this point. Is that what you mean? Or
I mean that when you
or the whole Minkowski space is connected.
that both. I mean both. I mean the fact both. The fact that when I move through space, right, from this location to that location, the fact that there's like some space in between that connects them is an indication that the space here and the space here are entangled. That's what this is supposed to be. So the fact that these two black holes are entangled means that there's some space connecting them.
You're asking about the firewall in Rindler, right?
Yeah, basically.
But these Rindler horizons are always sort of youngish.
Yeah.
So they sort of don't really fall. You cannot.
Yeah, Rindler horizons don't have firewalls. The firewall argument
They're
doesn't
young.
apply to
Yeah.
them.
Yeah.
Rindler horizons have infinite entropy, so they never lose half their entropy. The radiation they emit, there's no reason to believe that it has information. It should just be thermal. Yeah, so there are other things I should mention. So this ER equals EPR is nice, but that's not the only way to use ADS-CFT to try and address this question. I mean, whenever you have a question in quantum gravity, sort of the first thing you should do is to try and apply ADS-CFT to it, because that's where we have our best understanding of quantum gravity. So there's some interesting arguments specific to ADS-CFT about to what extent does ADS-CFT describe the inside of a black hole, right? So you could ask, is there, within ADS-CFT, just ask the CFT, is there a firewall? Right? That's sort of what we're getting at here, but we can sort of repeat the question with not a two-sided black hole, but just a one-sided black hole. So just in ADS space, So this is, so I'm going to use coordinates where the boundary is at r equals infinity, right? And this is the sphere at infinity. But this is not the boundary. This is r equals 0. Okay. This is the origin. This is the boundary. And, you know, we're going to create a black hole. Yes. And this is the diagram. And then it'll look, maybe it's a small black hole and it evaporates eventually. Maybe it's a big black hole and it doesn't. So we can ask, what operators would we use on the boundary to probe the inside of the black hole? Do such things exist? If so, you know, it seems like that, you know, if they exist, then it suggests that there's no firewall, right? I mean, you know, the firewall really is more like an end of space-time. Okay, so how do we look inside of the black hole? So there are, you know, there's ongoing debate about this actually in the literature. So there's some interesting arguments about why you can't see inside of the black hole. So I'll just sort of give those arguments quickly in sort of a heuristic way. So if we weren't in the black hole, let's say we were here, and I wanted to know what is a field operator here in terms of operators that live in the CFT on the boundary. Right? How would I do this? Well, ignoring questions of like local operators are not really well defined, et cetera, et cetera. Local operators in the bulk. The thing that I would do is I would do something very similar to, you know, I would solve equations of motion in the bulk, and I would use a Green's function type construction to figure out what the operators were out here. Okay, this is called the smearing function construction. It goes, you know, it's popularized by Bot of Schitz, Low, and company. So if I were going to do some kind of causal evolution, for example, what I could do is, because this, you know, let's stick to free fields. Let's say I wanted to know what the field operator here was, right? So causally, we know that this thing obeys some equation of motion. So classically, if it were a classical field, I could write the classical field value as an integral over field values here, integrated against the retarded Green's function, right? And the field operator satisfies the same equation of motion. So I can do the same thing with the field operator. I can say that the field operator here is equal to the integral of field operators along, you know, this thing using the retarded Green's function. Okay, that's fine. And you can do the same thing with any Green's function you have. So the interesting thing about in ADS space, one interesting thing you can do is you can construct Green's functions which effectively do space-like evolution. So you can write the field operator here in terms of field operators out here that live next to the boundary. Okay. And I mean, I don't want to go into the details, but there's a version of the ADS CFT dictionary, slightly different from the you know, sort more of a canonical quantization dictionary versus a path integral dictionary, which says that if you have local operators near the boundary, you know, asymptotically approaching the boundary, these can be directly related to local CFT operators. So essentially, what this lets you do is it lets you take a superposition of local CFT operators over, you know, smeared over this region of the boundary, and relate it to a local field operator here. And the key point is that this makes use of classical equations of motion of the bulk. Okay? So why not do the same thing out here? All right, well, first of all, if you had a point here behind the horizon, well, a space-like type Green's function won't help you because you'll run into the singularity problem. You know, you have to get out from behind the black hole before you can do that. So the natural thing to do is sort of combine do the thing in two steps. Do sort of a retarded Green's function operation. And in this diagram, it looks like I'm running into this wall, but this is the origin, so I can just pass through the origin. Do some kind of use some kind of retarded Green's function to relate